Here's an example of something called an exponential distribution. Pretty important example in statistics. Its probability density function, PDF, f of x, is an exponential decay function. Well, technically, it's piecewise still, just like those other examples. It's exponential decay, say e to the negative x, if x is greater than or equal to 0, and 0 if x is less than 0. So this is a function whose graph looks like this. 0 over here, then it jumps up to an exponential decay that looks like this. Actually, maybe I should have used t for the variable, because often in applications, the variable represents time. What kind of thing does this model? A common thing this models is wait times. What kind of wait times? Well, maybe wait time if you are sitting at an intersection and you're waiting for the next car to come through before you know the light's going to turn green after they come through. How much time do you have to wait till the next car goes through? Wait times till the next, we need to talk about sad examples. Earthquake, say, if we're in Southern California, causing damage. Insurance companies use this a lot to measure the amount of time between events, like earthquakes, hurricanes, that kind of thing. It's a simplistic model. For example, in Florida, hurricanes mostly just occur from, August through November. This model assumes they occur at a uniform rate throughout the year. It's, again, supposed to represent the amount of time. The scale here might be, x could be in years. And this would be like x is 1, x is 2, x is 3, etc. Say we're modeling small earthquakes in Los Angeles. What's a small earthquake? Like anything under 3 on the Richter scale, maybe. How much time do you have to wait until the next earthquake after one has just occurred? Well, there's the phenomenon of aftershocks, but we're ignoring aftershocks. This PDF, this density function, is supposed to model how long you have to wait. The fact that it's higher when x is lower means most likely you won't have to wait very long. Most of the time, the data for the amount of time you have to wait is relatively small, less than a year, say. But the probability density function is still positive over here, though small in value. What that effectively means is every once in a while, you might have to wait a long time, maybe over 3 or 4 years till the next earthquake. We're interested in finding probabilities. What is the probability that, for example, I might have to wait between 1 and 2 years for the next earthquake? And actually, in statistics, the amount of time you have to wait here is commonly written with a capital letter to distinguish it from the lowercase letter here. The way you find that probability, P stands for probability, is by doing an integral. These models are set up in such a way that when you integrate the PDF, the probability density function, over the interval in question, it gives you the probability. Which means we need the fundamental theorem of calculus, which means we need an antiderivative. The CDF is one antiderivative. I'll call it capital F, where capital F of x is the so-called CDF. PDF stands for probability density function. CDF stands for cumulative distribution function. It's not any old antiderivative of little f. It's one particular one. And in this kind of situation, it's the integral of little f from 0 up to x in this kind of situation. Integral of little f. What should I call the variable of little f here? Something other than x. How about you? Now you might say, well, why do I need to bother with this? Can't I just guess an antiderivative? And the answer is yes. In general, you could just guess an antiderivative, but we're trying to say the CDF is one particular one that is sort of more special than the other ones. Its value at x equals 0 will be 0, for example. And it's going to have a limiting value, it turns out, as x goes to infinity of 1, because the PDF can't be any old function. It's got to be chosen so that the total area under the graph equals 1. The total area under a PDF has to equal 1. Now, it's a little strange here because the graph goes out forever and ever. So how can that have a finite area? Shouldn't the area under it be infinite? The answer is no, it's not. It's finite. It's effectively finite because the exponential decay makes the graph go toward the horizontal axis so fast that even though the area goes out forever, the region goes out forever, it's got a finite area. Amazing. Okay, that can be proved involving doing a limit calculation, but just trust me, it's 1. And by making this function have a value of 0 when x is 0, like I'm doing here, I am making it so that its limiting value is also 1. Now let's do this integral. Antiderivative of e to the negative u by a little bit of guesswork is negative e to the negative u. Check by differentiation. U goes from 0 up to x. A little strange here. The variable for this function, capital F, is the upper limit of the integral, which over here becomes this upper limit. Plug in that upper limit first and subtract what you get when you plug in the lower limit. So you get negative e to the negative x plus e to the 0, but e to the 0 is 1. This is 1 minus e to the negative x when you simplify it. One particular antiderivative. And if you graph this, technically it's also a piecewise function. It's equal to 1 minus e to the negative x if x is greater than or equal to 0, and it's equal to 0 otherwise if x is less than 0. And if you graph this CDF function, it looks like this. It's 0 over here, and then it doesn't have a jump discontinuity like little f did. Instead, when you plug in 0 here, you get 0. It goes up like this, and it's got the line at 1, the horizontal line at 1 as a horizontal asymptote. It does approach 1 as you go to infinity. And that is a function now you can use to find that probability that we were interested in. The probability of waiting between 1 and 2 years for the next earthquake. It's capital F of 2 minus capital F of 1. If I want to use the CDF to do that, that's 1 minus e to the negative 2 minus 1 minus e to the negative 1. I'm plugging those numbers into the CDF. The ones end up canceling. This simplifies to e to the negative 1 minus e to the negative 2. That is a positive number, as probabilities have to be. E to the negative 1 minus e to the negative 2. It's about 0.233. About a 23% chance, according to this model, that we have to wait between 1 and 2 years for the next small earthquake of Richter scale magnitude, I don't know, between 1 and 3 or something. I'm just hinting at applications. Yes, insurance companies do use sometimes simplistic models like this to try to get rough estimates for how much their costs are going to be. It is simplistic because it is just focusing on, for example, Los Angeles, say, as opposed to also thinking about the rest of California. It is focused on just certain classes of earthquakes instead of all earthquakes. But it sort of hints at possible applications of this. But it is an application of integrals, antiderivatives, and it's something worth thinking about. I should also say the fundamental theorem of calculus, part 2, section 6.4, which I won't test you on, but I did mention the other day, says that when you differentiate an integral like this, capital F prime of x, you do get the integrand function, the little f, evaluated at the same number x. That's true for this example, and it's pretty easy to see. You can just differentiate this. But it turns out to be true in harder examples where the capital F function doesn't have a simple formula. Maybe this is the normal curve and you get ERF. Okay, maybe it's something else and you get something involving like that gamma function from the other day. The principle still works. And it's still a useful thing because you can still use numerical integration, Riemann sums, to approximate integrals and therefore approximate values of capital F. This is all stuff that people do. Let me end by saying that we can also simulate this to make it seem more real. Simulated in Mathematica here. I'm going to do that to make this seem a little bit more real. Enter these functions, and I've got a little program here that essentially simulates sampling from this distribution. If I let this slider here n increase, I'm going to see more and more data points representing more and more wait times until the next earthquake. Notice that the points are denser here in the smaller values of x, reflected by the fact that the PDF, the probability density function, is higher. Less dense over here, where the probability density function is lower. But still, once in a while, you have to wait a long time until the next earthquake. There's 100 data values here. What do I have here? I also have, there's the PDF here, and I have an area shaded. What is that area? It turns out it's the integral from 0 to 1, I think. 0 to, well, actually 1.1. This number here, 0.667, says that's the area under there. This number, this 66, says that for this particular simulation, 66 of the 100 data values are between 0 and 1.1, close to the probability of 0.67 as a proportion of the time that it occurs. If I run the simulation again, it won't necessarily happen in the exact same way because it's a new simulation. The area under the curve from 0 to 1.1 is still the 0.667, but now for this particular simulation, 71% of the data points are between 0 and 1.1. That's because it's a simulation involving randomness. This is what happens when you try to apply probability to real life, is it's not a perfect model, it's just an approximate model, but you hope it's good. You hope it's good enough to make decisions like business decisions for insurance companies, for example.